write in the chat. I think, yeah, basically everyone is still in. So maybe let's get started with Carsten, who is at Columbia. Go ahead, Carsten.
So first of all, I would like to thank the organizers for the opportunity to speak. So today I'm going to present joint work with Quentin Berger and Hubert Lacroix about the parabolic ANC model with Lévy noise. So I would like to start this talk by introducing the model. So what you can see here is basically the usual stochastic heat equation that I think many of you are familiar with. So we are working in d dimensions on RD with some nice initial condition U0. But the novelty here is somehow that instead of a Gaussian noise that we usually consider, what we do today is we consider a non-Gaussian noise. So the noise here, which I abbreviate with L dot, is a Lévy space-time white noise. So that's a noise that is discontinuous and is made up of atoms. I will introduce that a little bit later. So in front of the noise, I will also have a coefficient, which is a function of the solution. For the moment, it's a globally Lipschitz function, but later on I will specialize to the case where sigma is a linear function, so we have the parabolic ANC model. So for those of you who are not familiar with Lévy noise, let me give you a quick definition of what I mean by a Lévy noise. So to simplify the exposition, I will assume that the noise has a finite mean, first of all, and that this mean is 0. So we have a martingale type Lévy noise. So what is that? So basically what you do is you consider a Poisson point process, omega, okay, in time, in space, and then you also have a third component which describes the jump sizes. And the intensity measure is dt dx in space and time. And the measure that governs the distribution of the jumps is a Lévy measure lambda. And what you do then is basically the following. So you take a bunch of Dirac delta masses and you put them onto the space-time points that is, given by this Poisson point process omega, and you weight these Dirac delta masses by the jump size z. Okay, and then you sum up, all these Dirac delta masses. And what I do here is basically I only restrict to the jumps or the atoms for which the jump size in modulus is greater or equal to a being some small threshold. And this will ensure basically that this sum here is convergent, at least locally. So this is a well-defined measure locally. But of course, in the end, I would like to send a to 0. So what I do is I compensate this by subtracting the mean. So kappa a is the mean of this noise. And what you can show then is basically that when a tends to 0, under this compensation, you will have a well-defined limit. The only thing is that, whereas this measure is always, a random measure defined path by path, the limiting object, just like Gaussian noise, is typically no longer a path by path measure. Okay. All right. So before I present the results of this work, I would like to give you a short history on this equation. So what results are known so far. So the first papers that considered the heat equation with Lévy noise were published around 1998, I would say. And basically what they were able to prove is existence and uniqueness of solutions under a strong moment condition. So what is a strong moment condition? So the assumption is that you have an exponent p, okay, between 1 and 1 plus 2 over d, such that the Lévy measure integrates z to the p, okay? And this is a strong moment condition, in my opinion, because it rules out, for example, noises like alpha stable noise. So for alpha stable noise, for example, the measure has a density with respect to Lebesgue measure that is a power law. And in that case, so alpha is something between 0 and 2 strictly, you will never have this condition, right? So because here you're integrating over the whole of R, and this will not be satisfied for the important class of stable noises, for example. Now, what do we know for a stable noise now? So a first paper in that direction was a paper by Raluca Bala in 2014. where she proved, again, existence and uniqueness of solutions, but on bounded domains instead of RD. And the thing is, with bounded domains, basically, what you have is that if you're working on a bounded spatial domain, locally in time, you only have finitely many big jumps. Right? The property of a Poisson point process. So what that means is you can basically reduce the case of stable noise to the case where you have as many moments as you want, because locally you only have a finite number of big jumps. So you can pretend as the region just bounded by a large constant C. Okay. So using stopping time techniques, you can basically reduce the case of stable noise to this case. So that's a straightforward argument. When you go to the whole space, there are also two other papers that I would like to mention, one by Müller and one by Mitnick, where they consider solutions to this equation, but for a non-Lipschitz sigma. So it's this function x to the beta smaller than 1. And these type of equations are connected to the study of super Brownian motion with alpha stable branching. I won't go into detail in this point here, because the equations that we are going to consider are very different from this equation, because we have a Lipschitz function here. So actually we will consider linear functions. Now, what about Lipschitz sigma? In the general case of a Lipschitz sigma, what we were able to obtain in a paper in 2017 is the existence of solutions, provided you have this condition here. Now, if you compare this condition with the one that is stated above here, the difference here is now that you have two different exponents. So you have freedom to choose two different exponents, one P, one Q, one for small jumps and one for big jumps. The P and Q have to be related somehow. I don't want to go into detail here, so they are related, but you have a freedom to choose two different ones. And that in particular would cover, for example, all alpha stable noises with alpha between 0 and 1 plus 2 over d. So that's already an improvement compared to the original condition here. The latest development was in a paper by Berger and Lacroix in 2021, so it just appeared, where they look at a special case, and that's also the special case that we are going to consider in this talk, which is they specialize the case of the parabolic Anders model. So sigma is a linear function. They assume we have no negative jumps, so all the atoms that you get are positive. So that in particular implies that also the solution will be strictly positive, or at least non-negative. And the initial condition is the Dirac delta. Okay. Now what they were able to prove is now the following. So let UA, okay, be the solution to the heat equation with the truncated noise LA. So I remove all the atoms that are of modulus smaller than A. Only the ones larger than A are considered. Then what happens is the following. So if you can find a P again in this range, such that the Lévy measure integrates Z to the P. Now here, important, we are only looking at 0, 1. So that's only condition on the small jumps. Okay. So when I go back, this was on the whole space. So that's obviously much stronger. It's also, this one is also stronger because this imposes a similar condition on the small jumps, but it also has another one on the big jumps, which was removed in this theorem here. Okay, so this is only a condition on the small jumps. If I have that, then they could prove that UA converges almost surely to a non-degenerate limit U as A goes to 0. Okay. On the other hand, if you have too many jumps, in the sense that if lambda integrated against z squared log c in dimension 2, or against z to the 1 plus 2 over d in dimensions 3 or greater, if that becomes infinite, they were able to show that UA will converge to 0 almost surely, so you cannot have a non-degenerate limit. Okay. Actually, in that paper, the main motivation they have is to study the convergence of polymer measures with heavy tail disorder. So they considered an IID field, eta IX, so I discrete time, X discrete in space, with finite mean, and such that the probability that it's greater than -1 is 1, and a simple symmetric random walk on CD. And when they consider this partition function, what they were able to prove is that if you scale this beta parameter here appropriately, in the sense that you choose beta n in this specific way, you get convergence in distribution to exactly the solution to this heat equation that they found in the previous theorem. Actually, you have convergence to the total mass of this equation. So you integrate over RD, okay? And the assumptions they made is that these eta variables have a stable-like tail, Pareto-like tail, alpha between 0 and 1 plus G over D, and beta n has to scale like this one here. And this is basically a Lévy version or a alpha stable version of a well-known result by Albert, Kani, and Costel from 2004, where they did the same program basically for Gaussian noise in dimension 1, where the scaling was n to the -1/4. So if you take alpha to be 2 and d to be 1, that's exactly the 1/4 here, okay? So that is what is known until now. So now let me describe the results that we have. So the first results are about existence versus non-existence of a non-degenerate limit. So again, we consider the same situation as before. So parabolic Anderson model, no negative jumps, Dirac delta initial condition. We consider this the solution with this truncated noise, and we want to study what happens if I let the truncation A go to 0, okay? The first result, what we could prove is the following. So in dimension 2, okay, you have convergence to a finite strictly positive limit if and only if lambda satisfies this condition here. So the necessity part, okay, was already proved in this first paper by Berger and Lacroix. So the novelty here is really the sufficiency part. So this is a necessary and sufficient condition, okay? In dimensions 3 or greater, what we could show is the following. So if lambda integrates z to the 1 plus 2 over d log c, then we have convergence to a strictly positive limit. If lambda fails to integrate c to the 1 plus 2 over d times log c to a power that is a little bit smaller than 1, we get convergence to 0. So what that means is the following. So both conditions, this one and this one, they improve the previously known results for the previously known sufficient conditions and the previously known necessary conditions. But there's still a small gap between these two conditions. So we don't have a necessary and sufficient condition yet, although we conjecture that it's more likely that it's going to be this condition here. Okay. Was that a question or just some noise? Okay. Good. Next result. So, okay, let me go back one step. So what we were able to prove here, okay, is just convergence of UA to some limit, okay? An obvious question is, of course, does this limit actually solve the stochastic heat equation? I mean, that's not guaranteed a priori, right? And that's actually true. So under this condition that we imposed, we can show that the limit actually solves the stochastic heat equation in the mild sense. So it satisfies this integral equation here almost surely for each fixed t and x. In particular, part of the statement is obviously that these stochastic integrals here are well defined. Okay. Okay. Now, how do you may think that this is somehow obvious, right? Because the U8 with the truncation solves the same equation with an LA here. But in order to pass the limit, what is very important is that you have some sort of control over the moment. So the proof of this result is actually based on the following one. So this is about moments. So again, it appears to be expected, but I will comment in a minute why it's not so trivial to show. So if the Lévy measure, okay, the noise that you take has a finite pth moment, so that's expressed through this condition here, again p in this range, then the solutions will have finite pth moment, and this is uniformly in A, the truncation parameter. In particular, we can pass the limit, and we know that the limit will also have a finite Pth moment. Okay. Now, the remark that I want to make is the following. So, proving or showing finiteness of Pth moments for Poisson integrals is trivial, I would say, or easy if you have this strong integrability condition here. So if you have integrability of z to the p for both small jumps and big jumps at the same time. It becomes difficult, however, if you only have a condition on say the big jumps and a different one on the small jumps. Then it's a much more difficult thing to do. Okay. All right. So the last thing that I want to consider is what I refer to as intermittency. So that's basically about the large time behavior of the solution as time tends to infinity. So I will say that the solution is intermittent if these moment-Lyapunov exponents here are strictly positive. So in other words, if I look at the total mass of the solution and I take the Pth moments, if they grow exponentially fast, then I say that the solution is intermittent. Now, what do we know about intermittency? Well, there are many results that are known until now. So, for example, in discrete space, so if we just have, if we work on CD with Gaussian noise, in this famous memoirs paper by Carmona and Morjanov, we know that you have intermittency for all P and all beta if dimension is 1 or 2. While in dimension 3 or greater, you only have intermittency if beta, so beta is the constant in front of your nonlinearities, sorry, in front of the noise. So it's the strength of the noise. So if the strength of the noise is larger than some beta critical, you have intermittency, but you don't have intermittency if beta is smaller. Okay, so that's a well-known result. In continuous space, okay, so really, space-time Gaussian white noise, actually, you know everything that you want to know in dimension 1. So basically, you have an explicit formula for the moment-Lyapunov exponent. So there's a long story behind, this identity here. So it started in work by Bertini and Cancrini, and then there were many, many papers in between that I don't have the space to list. And I just mentioned the last two that I'm aware of, and these are exactly the same as Wei Tao mentioned in her talk just before, okay? All right, so that's for Gaussian noise, Lévy noise. So in the first paper with Peter K. we were able to prove the following. So in dimension 1, as in the Gaussian case, we have intermittency for all reasonable exponents for all beta. In dimensions 2 or greater, we were only able to show intermittency for large p, so large meaning close to 1 plus 2 over d, or large beta, or both. So if you compare, for example, with that result, you may say, this is expected because, probably you will have something similar. So we were only able to prove that we have intermittency for large beta, but we were not able to prove that we don't have intermittency if beta is small. Okay, so that's the current state of the art. The novelty or the new part of this work with Berger and Lacroix is now the following result. So you could prove the following. So if there's one thing, okay, that I want you to remember from this talk, it's going to be this. So the take-home message is with Lévy noise, actually, we have intermittency for all P, for all beta, for all dimensions. So it's not like with Gaussian noise, where typically you don't have intermittency for all betas in higher dimensions. With Lévy noise, you really have intermittency in any dimension for any value of beta. Okay, and we find that a surprising result if you compare, for example, with what is known in the Gaussian case. Okay, so let me quickly see how much time I still have. Like 5 minutes. Okay, I will mention this result, and then I probably will stop. I don't have time to go to I will skip the proofs. So the last result that I want to mention is basically, okay, we can not only prove you have intermittency, but we also have some control over how these intermittency exponents behave in terms of the intensity parameter beta. Okay, so in dimension 1, if you have a finite second moment, these exponents basically behave in the Gaussian case. So it's something to the beta times beta to the power 4, okay, like in the Gaussian case. In dimension 2, again, assuming you have a finite second moment, so if these two, this is just finite second moment, what we could show is that you have this limit. What that means is basically that gamma beta p behaves a little bit like e to the minus some constant beta to the minus 2. That's what it means. So we see in particular for any beta, this is positive, but it's exponentially small. Okay. We have a similar result for in dimensions 3. So given these moments, we have that the exponents here behave like e to the minus c b to the minus some exponent, okay? And we know that this exponent is between 1 plus 2 over d and 2. That's what we can show for now, okay? Now that is, of course, all these 3 results hold if you have some moments, right? In particular, if you have stable noise, you don't have this. So in a stable case, actually, it's much simpler. In a stable case, so if lambda has the stable tails, what you can show is actually this, which means that gamma beta p is roughly constant times b to the alpha over this 1 minus d over 2 alpha minus 1. And again, if you specialize to the case alpha equals 2 and d equals 1, you're back in this case. Okay, so so what we see here is basically the tails, the upper tails of the Lévy measure has an effect on the intermittency exponents. Okay. All right, so maybe I can spend 1 more minute on the proofs. So okay, upper bounds and lower bounds. So for upper bounds and lower bounds, the strategy of the proofs are very different. So for upper bounds, the main tool is, of course, using a chaos decomposition. So you write your solution as a series of multiple Poisson integrals. Now, what you have to do is you have to estimate all these multiple Poisson integrals. And the problem with Poisson integrals is they're typically difficult to handle. So a main tool or important tool that we use is decoupling. So what you can show is if you have a multiple integral like this, okay, with the same noise L. So I threw out space to save space, otherwise it wouldn't fit on this slide. If you have the same noise here, k times, you can actually replace it by k IID copies, okay? And you only lose a constant. That's decoupling, okay? And if we do this, what this will mean is we can actually change, the order of integration. So we can switch all these L's around. We can first integrate with respect to T5, then with respect to T2, and so on and so on. So this allows us to choose an optimal order of integration, and that will help us in deriving these, upper bounds for the heat equation with Lévy noise. So that's the main idea for upper bounds. Okay, for the lower bounds, I think I don't have so much time left. So let me just say this, okay? It's not written here. So the main idea behind the lower bounds is you need to find a functional f, okay, such that its expectation is relatively constant. But if you add specific points to the Poisson point process that you already have, that the expectation becomes much, much larger than it was before. So that's roughly the idea. So I don't have time to go into that into detail. If you're interested, please feel free to reach out to me. I can explain that in more detail. So as I'm running out of time, I will stop here. Thank you for your attention. And these are the references that were mentioned in the talk. Thank you very much.
Well, let's all thank Carsten. And are there any questions? We have 5 minutes for questions and discussion. If not, Carsten, I don't know whether you want to actually say a few words about the lower bone, because we do have a few more minutes.
Sorry. I thought I would just have. Okay, good. Now I have time for a lower bone. Okay.
Yeah, I think the next talk is supposed to start at 11:40, so we have time.
Oh, okay, good, great. So for the lower bound, the main idea is to use the so-called size bias representation that was introduced in this paper by Berger and Lacroix. So the idea is this: you consider a new probability measure, okay, P tilde, which basically has a density with respect to the original measure, where the density is given by the solution to the heat equation, so the spatial, the total mass of the solution. Okay, and now what you can show is you can characterize this new measure. So if you change to this new measure, what actually happens is you add additional points to your original point process. So you add an independent point process, omega prime, with a specific intensity on the path of an independent standard Brownian motion. So let me visualize this. I think it's easiest if I draw a picture. So let's say these are your original points, okay? That's omega under the original measure, P, okay? Usual point process. Now, omega under P tilde is this. So you added a Brownian motion independent of everything, okay? And you add additional points on this path, okay? That is the description of omega of the point process under this new measure. Now, what you want to do is you want to find a functional, okay, a random variable, such that its expectation under this new measure is much larger than, first of all, the standard deviation of the same functional under the original measure, but also much larger than the variance, or sorry, the standard deviation under the new measure. If you're able to do that, basically what you can show is the two measures. So the original measure and this new measure become more and more singular as, say, time goes to infinity. And that will, using some arguments, in the end give you intermittency. Or if you do it on a finite time interval, degeneracy of the limit as a goes to 0. So that's the main idea behind this lower bound. And maybe as the last word, so the typical f that we take is this complicated thing. So I can maybe describe, in a picture what that means. So basically what you want to do is, okay, so if this is time, okay, you want to find clusters of points that are close to each other. So you want to find k points that are close to each. Okay, so it's maybe not that good. So they should be, so it's only in time. So k points that are close in time. Then you have a gap, and then you want to have another k points that are close, another gap, and then another k points. So this is what will give you intermittency in dimensions 2 or greater. If you're in dimension 1, or if you have this the stable tails, so really big jumps, it suffices to just take one point here, 1 point here, 1 point here, and you will have large enough blue points that will give you intermittency. But if you have light-tailed noise and you're in higher dimensions, you need a bunch of points to give you one peak. That's the idea behind the proof. Okay, so now I think I'm really running out of time. Thank you.
Yes, thank you so much again. Maybe the best thing is if you guys reach out to Carsten later on, because indeed we need to get ready for Ling Fu's talk. Ling Fu, would you like to